Hello everyone and welcome to week 3. Starting from week 3, we will dive deep into the first domain of using deep learning, which is computer vision. Now, computer vision is defined as a field of study that seeks to develop techniques to help computers see and understand the context of a digital image, such as a photograph or a video. Computer vision is certainly not a relatively new scientific field. In fact, computer scientists around the world have been trying to find ways to make machine extract meaning from those visual data for about 60 years now. So definitely computer vision is not a new field. But the breakthrough in computer vision happened recently. That was in 2012 when AlexNet, which is an architecture, which is a neural network architecture that was designed, won the ImageNet competition. Now you might be already familiar with Kaggle competition. So in Kaggle competition, you have the problem statements from all domains. So it could be simple machine learning problems, it could be problems with images, audio, problem statements related to a recommendation system, and so on. Or it could be problem statement related to NLP. So in Kaggle you find a variety of problems, whereas in the ImageNet competition it is more devoted or inclined towards solving computer vision problems. So all the problem statements that you find in the ImageNet competition will be associated with computer vision. So the most recent breakthrough happened in computer vision in 2012 when this architecture called as AlexNet won the ImageNet competition. So we will discuss about all these architectures during our weekly lectures. Now, there are often people who confuse between computer vision and image processing. In fact, computer vision is very different from the normal image processing technique or the common image processing technique. So, image processing is the form, or it is a process of creating a new image from an existing image, for typically simplifying or enhancing the content of the image in some way. It is a type of digital signal processing, and it is not concerned with understanding the content present in the image. So that is the difference between computer vision and image processing. So computer vision is associated with understanding the content or present in the image. So for example, if you have an image which has a cat in it, the computer vision is the idea of computer vision is to identify that cat, that object present in that image, or the content present in that image. Whereas image processing, it is more inclined towards creating new images from existing images by just simplifying or enhancing the content in some way. So that's a major difference between the two. But of course, in order to build a computer vision model, we always require an image processing at the at the very beginning, right? So we have image processing, and then after that we build our computer vision problem. So it's something which goes hand in hand, but definitely there is the difference between the two. For example, image processing include more like normalizing the photometric properties of images such as brightness or color. Other example of image processing is cropping the bounds of the image such that the object present in the image is almost to the center of that photograph, right? Also, another example of image processing is removing digital noise from the image. So these are all examples of image processing, and it is usually done before actually building your computer vision problem. Now, definitely there is a fast growing collection of useful applications from the field of computer vision, like definitely the facial recognition, image retrieval. It is used in gaming and control, biometrics, surveillance, and also in smart cars. So basically, for our purpose of study, we will divide the type of computer vision problem into 4 categories, of I would say 2 categories, which is further divided into 2 category each. For example, we have single object problems and multiple object problems, and in single object problems we have classification problem as well as classification plus localization problem. So as you can see from the figure, the difference is very clear. Classification is identifying the object present in this image, whereas in classification plus localization there is a bounding box prepared or created around that object in the image. And in multiple object problem, we will look into object detection and instance segmentation. So before we actually think about designing a computer vision problem, we should understand how machines interpret an image. So this is an example of a grayscale image. So as you can see, the machine interprets the image as a series of pixels, and each pixel is represented by a number from 0 to 255. And it is this series of numbers which we see on the right of this slide is what the software or computer vision software sees when you input an image. So image is nothing but pixel. Pixel is nothing but a collection of numbers from 0 to 255. Now this is an example of a grayscale image. Of course, when you have a color image, you have red, green and blue RGB channels. So instead of just one square like this, you will have a depth of 3 which represents red, green and blue. Promise of deep learning for computer vision. Now, understanding the latest advancements in AI can seem overwhelming, but in reality, it just boils down into 2 popular concepts, which is called as machine learning and deep learning. But lately, it is this deep learning which is gaining much popularity due to its supremacy in terms of accuracy when trained with, of course, huge amount of data. And the reason for this is that our traditional machine learning algorithm need a lot of domain expertise or human intervention, and is only capable of doing what it is designed for. For AI designers and the rest of the world, this is where the deep learning holds a bit more promise. Practically, deep learning is a subset of machine learning that achieves greater power and flexibility by learning to represent the world as nested hierarchy of concept, with each concept defined in relationship to a similar concept. For example, a deep learning technique learns categories incrementally through its hidden layer architecture, defining low-level categories like letters first, then high-level features like words, and then higher-level features like sentence. Or in short, the machine learning does not have automatic feature extraction, whereas when it comes to deep learning, it has automatic feature extraction, which itself makes the deep learning more powerful than a machine learning algorithm. One of the main challenges of computer vision problem is that its input can get very big. For example, imagine that you have a image of size 64 cross 64 and it is a color image. Now in that case, if I multiply 64 into 64 into 3, you get 12288. Now that is the dimension of your input space. So that is the problem with computer vision. In computer vision, you can have a very large input space. But again, when you consider a 64 cross 64 image in a computer vision problem, it is actually a very small image, but still it has this much input space or this much dimension for its input space. In reality, often the images that we will have to deal with is 1000 cross 1000, which means it has approximately 3 million dimension in its very first layer, which is the input layer. So that is one drawback of dealing with a computer vision problem. Convolutional neural network, or otherwise called as CNN. Now, CNN is a very specialized and a specific architecture used mainly to solve computer vision problem. We will soon understand why we don't use our traditional neural network as something like this in order to solve a computer vision problem. And this has something to do with the size of the image. So we use convolutional neural network to solve computer vision problem rather than a fully connected traditional neural network as like this. Now let us look what is the drawback of a traditional neural network which prevent us from using traditional neural network to solve a computer vision problem. The reason is that imagine you have a fully connected neural network that takes in an image of size 256 cross 256. And suppose this image, so usually in order to represent an image like this, we flatten that image. So this is how it will be fed into our traditional neural network. So suppose we have a 256 cross 256 image, and this image has to be fed to the first layer of our traditional neural network, which has, say, 10 neurons. In that case, the number of parameters or the weight that has to be learned by our traditional neural network at that point becomes 256 cross 256 into 10. That is approximately 655,360 weights or parameter. So that is a very large number of weight to be learned in just one layer of your traditional neural network. And imagine the number of hidden layers. We have, say, 5 hidden layers in that neural network. So imagine the total number of weight that this traditional neural network has to learn in order to train using a image as the data set. So basically, since our image are usually of larger size, and our neural network, our traditional neural network has to learn lots of parameters for those images, what happens is that we have a very large amount of computation that has to be done in order to get a small problem solved with an image. Now this is where convolutional neural network comes into play. A convolutional neural network is a clever way to reduce the number of parameters. So here, instead of dealing with a fully connected network, the convolutional neural network approach is to reuse the same parameter multiple times. Or the big idea behind CNN is that a local understanding of an image is good enough. So the practical benefit is that, of course, having fewer parameters greatly improves the time it takes to learn these parameters, as well as reduce the computational time of our model. So in a CNN, instead of a fully connected neural network of weights from each pixel, what a CNN does is that it just have enough weights to look at a small patch of the image. It is just like reading a book by using a magnifying glass. So eventually you read the whole page, but at one moment you only look at only a small patch of the book at a given time, right? So that itself is the idea of having a CNN, or how a CNN architecture works. For example, consider again an image with 256 cross 256 pixel. Instead of your code processing the whole image at once, it can effectively scan in chunk by chunk, say 5 cross 5 windows of that image. And then the 5 cross 5 window slide along the image from left to right as well as from top to bottom in order to actually read that entire image. So, in short, the CNN make this assumption that capturing this local pattern with just a 5 cross 5 window is sufficient to characterize and to reduce the number of parameters in a neural network. So that is the basic idea behind a convolutional neural network. Or in short, we have a very specialized architecture to solve problems related to image, or to build models which take image as its data set. And that architecture is what is called as a CNN, convolutional neural network.